Morning. It's 11 o'clock, so we'll start. My name's Jim. I'm one of the researchers here at the museum. I'd like to welcome you all to this week's installment of the Royal Tyrrell Museum Cooperating Society Speaker Series. Today we are hosting Dr. Dave Greenwood from Brandon University, who will be talking about plants, although there are a few gratuitous fossil insect and vertebrate slides in his talk. David is a native Australian. He born and raised in Adelaide, which is the capital of the state of South Australia. He has botany degrees from the University of Adelaide, Bachelor of Science honors, and a PhD. David tells me that in Australia nobody does a master's degree, or if they do, they don't admit it in polite company. And following his graduation, Dave has held a number of teaching research positions at various institutions in Australia, Fiji, the US, and in Saskatchewan, where I actually met him when I was just finishing up my undergrad degree in 1989 at the University of Saskatchewan, and Dave had started doing a postdoc there with Jim Bassinger. Since 2004, Dave has been a professor at Brandon University, where he has helped establish several graduate programs and continues to teach and do research. Dave's PhD work in Australia was looking at leaves that accumulated in the floors of modern tropical rainforests in Australia, and he was particularly interested in trying to understand how these leaves were deposited. So, for example, how far leaves would tend to fall from trees, and to use features of the leaves like their size, shape, and the veins to determine the local growing conditions. And both of those areas have great relevance to understanding leaves in the fossil record. And most of Dave's work since then has been focused on those areas. Because he works on angiosperms, he's stratigraphically limited to the Cretaceous and the Cenozoic. Has done a lot of work various places around the globe, in Australia and in Canada, in the Arctic and British Columbia. And today Dave is going to be talking about a lot of his work in the Eocene of British Columbia. So, Dave?
Thank you, Jim. First of all, I'd just like to express my thanks to Jim for organizing this, being a part of the Tyrrell Museum Speaker Series, being given a great welcome here, and also to the Pat and the Friendship Society for all their assistance in bringing me here. Okay, so the Eocene. What my talk's going to be focused on, in particular on a series of fossil floras which I've been working on with various collaborators over the last 10 years in particular. Just before I move on from my title slide, this scene is actually from Florida, but it kind of captures some of the kinds of environments that we are reconstructing for the Eocene in British Columbia. So where do we find Eocene floras in Canada? Well, as Jim mentioned, I started my professional work in Canada looking at some Arctic floras up in the high Arctic. And if we look on the top panel of this slide, we can see Ellesmere Island in this red square, and also Axel Heiberg Island, and with this perception given from the plant and animal fossils of these lush forests growing at high latitudes. So this Eocene world, which is very, very different to what we know today. Down in British Columbia, where I'll focus my talk, we have a series of fossil sites spanning the entire province, but concentrated down in the south. And whereas we know a lot about the plants, as I'll talk to you about this morning, we're also starting to know now a lot more about the animals. And I'll come back to this panel there showing the animals a little bit later in the talk. So why the Eocene? Why my focus, and why are paleontologists and others interested in the remote past interested in the Eocene? This plot we have here on the screen, which is somewhat famous now, the so-called Zachos Curve. We have time in millions of years running from about the end of the Cretaceous, or the extinction of the dinosaurs, running through to the present day. And we have a series of data from oxygen isotopes from the microfossils in the marine record, which is a proxy for ocean temperatures. And what we can see is that over a series of steps, the world gets colder relative to the Eocene. The Eocene represents a period in the geological past when we had very high global temperatures, ice-free north and south poles, with these forests, as we saw in the previous slide, up in the Arctic, but also, of course, across Canada or the US, we have these much more tropical-like floras and faunas. The sites that I'll be talking about this morning are focused in this particular very warm interval we call the early Eocene climatic optimum, which was a sustained period of global warmth caused by naturally high levels of greenhouse gases in the atmosphere. So the story of the last 50 or so million years is in fact declining temperatures with some reversals, and I'm going to focus on this time here where we have this selection of floras and faunas in British Columbia. So in this Google Earth image, we can see a collection of famous and not so well known sites ranging from Kushana near Merritt, British Columbia, around the town of Princeton, a big cluster of sites, some out near the Dominion Radio Observatory. Perhaps if you've ever gone out the Okanagan way, you've seen that. And also a cluster around metropolitan Vancouver and up around Kamloops and a little bit further north in the Thompson River Valley. Majority of these have a long history of study going back to the 1880s and 1890s, and I'll briefly sketch in the next slide that history. In focusing in on Vancouver, just very, very briefly, I want to just sort of highlight that these sites, which are mostly uncollectible now because we have, skyscrapers, highways, freeways, housing developments. We're not going to knock down a $2.5 million modest little Vancouver home to dig up fossils. But nonetheless, in the 1880s and 1890s, when early construction of infrastructure was occurring, and right through into the 1950s, fossils were being dug up, and luminaries of Canadian geology and paleontology like Sir William Dawson and his son George Mercer Dawson working on these floras, and later contemporaries of theirs, and then kind of a hiatus. The reason I mention these Vancouver ones is because they show a set of fossil plants which I would consider fairly typical for mid to low latitude. So down into Washington State and down through into Colorado and Wyoming, where we find these palms. And when we think about palms in the modern world, we tend to think of them as tropical plants. But as any Vancouver resident will tell you, well, I can grow them in my yard, Dr. Greenwood. And that's true. Palms do have some tolerance of cold, but they do have a fixed limit. And when we see these palms in the Vancouver area in the Eocene, it's telling us that certainly around there it was fairly warm, perhaps subtropical, and not unexpected for the early Eocene warm global conditions. However, in the interior, it's a different story, and that's where I'm going to focus my talk for you today. The interior floras have a long history of study. And through that long history of study, there's been a shift in emphasis as methodologies have changed, as our understanding has changed, as the kinds of questions we are interested in have changed. So as I mentioned in my introductory remarks, study of these sites, and they're all shown here with these open circles inside the green ellipse, going back to the Dawson father and son, the late 1870s through to the late 1890s, and then work by later workers such as Penhallow and Berry. And then in the 60s and 80s, through the 80s, some work on paleontology, so the pollen and spores, and some important discoveries. Some of you may be familiar with the water fern or mosquito fern Azolla. Certainly people can buy it in aquarium stores or gardening stores. This little floating fern is a very common fossil found through these sites, first recognized by Dawson and Penhallow, but then better resolved by Arnold from the University of Michigan and Hills and Gopal from the University of British Columbia. Into the 70s and 80s, we had people like Mark Wilson looking at the fossil fish in these sites, and Mark Wilson is very important in our story because he alerted us to a number of these sites which we perhaps were not unaware of, or perhaps have been lost through a passing of one generation to another. Jim Basinger, my longtime friend and collaborator. I always have to be nice about Jim because he introduced me to my wife. Got to say good things there. But Jim and Gar Rothwell and then Ruth Stockey and her students very much focused on the three-dimensional preserved Princeton chert site where you section the rock and you see beautiful anatomical detail. Now that shift with looking at the chert moved away from the typical floras that I'm going to talk about today. The typical floras which are perhaps what you might expect in terms of fossil plants. You split some shale, there's a beautiful leaf or a flower displayed on the rock. These are the floras that the older generation of workers were focused on and were somewhat passed over with this focus on the beautiful Princeton chert flora through the late 70s and early 80s. In the 1990s and 2000s, however, some of a new generation of paleobotanists shifted back to those shale floras, and in particular wanting to know what kinds of plants they were and their evolutionary relationships, and tease apart an interesting story that comes from this set of floras, because these floras fall at a critical time in Earth history. This warm period I mentioned in my first couple of slides. And that interest in it being a warm period is where I come in, because as Jim said in his introduction, one of my interests is climate and how we can tease that out from the plant fossil record, in particular using the morphology of leaves. A necessary little bit of geology to anchor our story is that those earlier workers we saw on the previous slide had long considered these floras to be, in the very beginning, workers like Dawson and Penhallow, that they were Miocene, so about 16-20 million years ago. Then, through Mark Wilson and others' work, considered to be Middle Eocene, so about 48 million years ago. We now know through some changes in our understanding of where the boundaries of different epochs fit, so the Paleocene-Eocene boundary and the Eocene-Oligocene boundary, and also the boundaries within the different subdivisions of the Eocene. Like taxonomists interfering with the names of plants you might be familiar with, stratigraphic geologists like to move the boundaries of the different epochs of time as their understanding improves. We now know through a combination of radiometric dating and fossil evidence that the majority of these interior British Columbia floras are in fact early Eocene and therefore coincide with this major climatic warm period, the early Eocene climatic optimum. So I just wanted to make that point because they sit in this warm period, they're important to us for understanding climate, but also understanding the evolution of temperate forest plants and communities. Now this complicated looking slide I'll tease apart for you for the essential detail. So there's our green ellipse then capturing those different fossil sites. You can see lots of red numbers. We can really just focus on the average. They're coming out at about a mean annual temperature of 10. What does that mean? Well, Vancouver is probably a good analogy for you. Vancouver's got a mean annual temperature of 9.9. In terms of winters, we use the coldest month mean temperature, CMMT. We're showing consistently across these different floras, reconstructed from the plant fossil evidence, that winters were mild. Doesn't mean no frost, doesn't mean it never snowed, but certainly you wouldn't have snow lying on the ground more than perhaps a few hours or a day or two, and it certainly did not have ground frost. Warm enough just to allow plants like palms to persist in the landscape. It was also very wet. Around 100 centimetres per year. Again, if you want to anchor that in something that you might have experienced, that's about what Vancouver gets. But less than, say, Abbotsford, or certainly a lot more than Drumheller. Down on the coast, however, those palms we saw earlier from Dawson's work around Vancouver and down into Washington, much, much warmer, more like, say, Los Angeles temperatures, or San Diego, or if you want to do it on the East Coast, South Carolina down into northern Florida kind of conditions. Very warm winters, very wet. So what we have then between the coast and these interior floras is quite a different climate. And what that means for us is that whereas it's kind of subtropical and warm and wet down here on the coast, in these interior sites, which have been reconstructed to be about 800 to 1,200 meters in elevation, similar to what they are now, it's a cool upland in an otherwise warm and wet world. So hence my title, Temperate Islands in a Warm World. And that is interesting for us because it means that up here, temperate kinds of plants were diversifying and becoming important in these cooler upland landscapes. Now, as I mentioned in my introduction, we've known about these floras for a very, very long time. This is the kind of thing paleobotanists used to do, and I'm sure it turned off many a generation of young persons seeking a career, as they would sit there and they'd draw these lovely detailed line drawings. And I have my poor old grad student doing that right now. He's got to learn the trade. But, you know, this is from work from Berry, 1926, American paleobotanist, found by geologists by the name of Uglow, Canadian Geological Survey work. That early work does remain current. People have gone back to those collections. In fact, I was doing that myself yesterday, and we find things that we didn't know were there before. The earlier work does not become dusty and forgotten. It does continue to have relevance for us. Horsefly is a site just in the centre of the province, famous from work by Mark Wilson from the University of Alberta and his students, and also Alex Wolfe and his students. These beautiful diatoms, but also beautiful insects, and the fish, of course, was the work of Mark Wilson and his students. And the thing about horsefly, and this is true of a number of the other sites, is these are lake beds. And a lake will deposit year in, year out, a thin layer of sediment. And every year it's capturing some leaves that become fossilized, some pollen, these diatoms, the fish, and horsefly is famous for these very fine laminations and reconstructing evolution of fish populations, the ecology of the system over decades to thousands of years, rather than our usual perspective in the fossil record of millions of years. Getting more towards where I'm working down around Maccabee and 1 Mile Creek, which is just near the town of Princeton. Again, long history of study going back to Dawson and Penhallow. The late Len Hills from University of Calgary did some work with his students on pollen and later on leaves. And then we have the later generations, including Sir Peter Crane, Ristocki, Kathleen Pigg, and others, Steve Manchester, focusing on reconstructing what kinds of plants were there. And I'll just very briefly, here we have a flower inflorescence up here in detail here, and here we have some fossil leaves compared to a living example of the same thing. And the reason I picked these particular two, Trichodendron and Tetracentron, is these are plants that are from a family and genera of trees which are found today only in China and adjoining parts of Eastern Asia. And it's a common pattern we see. There are plants that were common in these floras then in the Eocene, which are extinct in North America today, but still survive in China and adjoining parts of East Asia. These form connections between that continent and ours. This is another example. This is a seed or a fruit, if you prefer, given that there's usually two together. This is a plant called Dipteronia. Now, why am I showing you these fruits? Because they're common across these different floras, but again, it's showing that same story of plants that are extinct today in North America, but still persist in East Asia. And they're interesting apart from that point because they're typical temperate forest plants in Asia where they're found today, and they are part of this story of an emerging temperate flora in these highland areas in an otherwise warm world. And they're related to maples. Bit hard to see. We look in the colour photograph in the top panel, but it's somewhat similar in style, these fruits, to the samaras of a maple. Looking forward, this is the site which is called Thomas Ranch by more recent workers, but used to be called Tullamarine Road. Another one of these sites which shows these temperate links. Just wanted to show the examples of some fossils. We have ginkgo. Some of you may be familiar with ginkgo. I'm not sure whether you still have a ginkgo in your Cretaceous garden. There's that floating fern, Azolla. Here we have a sequoia. So there's a connection with modern day temperate forests of North America and California. We have pines. We also have fir trees and some weird Asian things. Like here we have Glyptostrobus, and the number 8 there. We have this thing called Taiwania, number 1 there, which again, these are conifers restricted to East Asia today. Metasequoia, the dawn redwood, again restricted to China today, but present in these floras at this time. Some other examples, we have oaks, we have maples, we have alders, we have birch, we have sycamores, we have elms. This is sassafras. Sassafras is a common deciduous tree in southernmost Ontario down through the Appalachians to as far as Florida. It's also in East Asia, in places like Taiwan and Japan and China. So again, these connections between East and West. And there's a little insect just creeping in there next to that oak leaf there. Okay. So moving forward to my own work. This is the Falkland Site, which is one of these sites that was brought to our attention by Mark Wilson. And there's myself in 2003. Please don't take my picture, I say, but he took it anyway. All these sites have characterized by these beautiful fossil fish that Mark Wilson and his students studied over many years. There's our team. This is Robin Smith. It's her PhD work. And Jim Basinger, who we've mentioned a couple of times, and her field assistants there working at the Falkland Site. Falkland Site is one where Robin, for her work, she, like we saw at Horsefly with the laminations, and we therefore have the opportunity to look at time in more ecological terms as opposed to geological terms, she sampled up through the section over about 3 meters of depth, so about 10 feet. And that means she's capturing about 6,000 years worth of time. And so any changes in the types of plants she finds lower down versus going up sections or getting younger are dealing with ecological processes, so forest succession, recovery after disturbance. And perhaps you can just make out where the hammer is sitting. This here is actually a thick volcanic ash bed, a tuff, or converted into a bentonite. And so we in fact have this lake community, the plants growing around the lake, responding to disturbance like the volcanism in the area. These are the kinds of fossils she was finding, fairly typical of these interior cooler upland sites. There's our metasequoia, there's our ginkgo, some ferns, we've got fir, we've got ash or fraxinus, we've got elms, and there's a fruit of an elm. We also have things like alders and cherries and some weird exotic, these Asian things. Again, this is the Chinese rain tree, which perhaps you know as a garden ornamental, and was growing here in BC in the early Eocene, but now only found in East Asia. And there's a maple fruit just there in the bottom right-hand corner. Okay. What does all that mean? What did Robin find in her doctoral work? Well, I'm going to tease apart this panel for you, and there's 2 different parts to our story, and it tells us something that is general across all of these cooler upland early Eocene floras, these temperate islands in an otherwise warm world. This is from the bottom of her sampled section to the top, so from oldest to youngest. And the thickness of these black bars on the right-hand panel there is telling us the change in relative abundance, how many fossil leaves we're finding as we count through. And what she saw was that there are definite changes. Some things become very abundant, other things decline, things appear that were not there before. And this is not evolutionary change, this is ecological change. This is at the scale of hundreds and thousands of years where the forest is responding to, in this case, there's our ash layer, volcanic disturbance. But what's also interesting is this horrible looking panel on the left. This is the easiest way to think of it is how many species you will encounter as you continue to count. A highly rich, highly diverse plant community is going to have a curve like this that is fairly steep. A plant community that is very low in diversity is going to have a shallow curve. And what we found with Robin's work and looking at the other sites is that the diversity in these cooler, upland, early Eocene temperate forests was very high. It was more like the tropics. So rather than thinking of, say, like a forest we might find in the Appalachians or in South Carolina or something like that, we perhaps should be thinking about something like the cool uplands or highlands of Central America, like southern Mexico or Guatemala, where we find these temperate islands in an otherwise tropical environment. So, Falkland. Oops, one too many. We also looked at the pollen. This is more recent work, just coming out in the Canadian Journal of Earth Sciences, so we can look at the pollen. The pollen allows us to have more finer sampling, and we're seeing a similar story. I appreciate it's a very complicated diagram. Here's some examples of pollen across the top. We've got various kinds of conifers and some angiosperms as well. But again, the important story here is that this work with the pollen by Patrick Moss, working with Robin and myself. Patrick's at the University of Queensland in Australia. But we're seeing this same pattern of the plant communities responding in time over sort of decades and hundreds of years scale to local environmental change. As Jim forecast in his introduction, I will show the occasional gratuitous animal fossil. Here's the first of more to come. This is the Driftwood Canyon site up near Smithers, one of the prettiest towns, in my opinion, in British Columbia. This site, the Driftwood Canyon site, is actually a park. It was actually unusual in the sense that the park was declared by the province in 1967 to provide an opportunity for the public to collect fossils. Unfortunately, people were too vigorous and they've had to withdraw that in the last 5 years, but it is a famous site producing wonderful, beautifully preserved insects, but also wonderful plants. And then in 2011 and 2012, my students, they were supposed to be looking for plants, and one of them found this beautiful tapir jaw and also some other interesting things. But before I move on to that, just what I want to talk about briefly, like we see with the Horsefly site and also Falkland, we have these stacked layers of lake sediments, volcanic ashes, allowing us to have some time control, but capturing this pattern of ecological time as opposed to geological time, seeing patterns of change in the plant communities. It's a pretty ugly place. I'm of course joking. It's a beautiful, beautiful site. This is the Driftwood Creek. The site you saw in the previous slide is actually to the right of this scene, just out of view. This is a site we discovered where we're there. Then we went back in the literature and discovered it had been discovered by other people in the past, but didn't tell anyone. Lovely leaves coming out. I wanted to show this side in part to show this gentleman, Clement Bertali from University of Utah, who had joined me in 2011. And the reason Clement is important is because he was actually sampling for geochemistry. About here is a sandstone layer and there's coal below it. And he had his pickaxe in his hand, and as his pickaxe descends, he shouts out, "There's a jaw!" And that in this little panel in the right corner here, you can see there's a very nice straight line there. That's where the pickaxe hit. The specimen, the two halves, went tumbling down to the creek, that previous slide we saw. And Clement, being the loyal graduate student, charged down, risking life and limb to save the specimen. He managed to save this piece shown in his supervisor's hands there, but unfortunately the other part was lost. This was described by Jaylene Eberle, Vitaly Rybczynski, and myself in 2014. Jaylene went back with me in 2012 to see if she could find more of the animal, but unfortunately we were unsuccessful. That find, sometimes your career goes in a little different direction for a little bit of time. I'm a plant worker, as Jim mentioned in my introduction, but of course I got caught up in the excitement of this discovery. There's that tapir jaw with the pickaxe cut in those cliff sites we saw in the earlier image. See here this little jaw, Silvicola acaris on the left of the panel. It's about the size of your thumbnail. And a student, Megan Gilbert, had the eye. She just happened to find this thing, needle in a haystack. We worked with our artist, Julius, and he produced this wonderful art for us, reconstructing the Driftwood Canyon ecosystem, so all the interesting things, the plants, of course, and the less interesting insects and mammals. Of course, I show my bias. But I want to talk just very briefly about this because it is, I think, an important outcome of my work and my collaborators, and that is to literally paint a picture to allow people to transport themselves and see what it was like, or how we think it was like, back then in the early Eocene. So we have these various insects, such as the green lacewing here, which has been named after the original custodian of the site. Of course, the tapir, or it's an early tapir relative, Heptodon, and this little early hedgehog, sufficiently early in the evolution of hedgehogs that it has some features you wouldn't associate with living hedgehogs, such as potentially having a tail and having more fur and less bristly. Got a lot of publicity out of that. It was quite the roller coaster ride. I was telling Jim, I was standing in my basement with 2 inches of water. Brandon was experiencing floods, and I'm getting the press calling me from all over Canada saying, could you give us a comment? And I said, well, just give me a minute. I've got to turn the pump off. But that's life in Western Canada, right? Okay. I just wanted to show this slide because one of my personal frustrations is that there's beautiful bird fossils known from these sites. The one on the top left panel was collected by Pat Petley, a resident of Kamloops, in 1968. It's sitting on display at Thompson Rivers University in Kamloops, and we keep trying to get someone to describe it and name it. This is another one collected in Driftwood Canyon in 1965, I think it was, by German tourists. They took it to Germany. Grandpa died, sitting in the basement. Fortunately, it was returned to British Columbia and is now in a museum. So we have these additional lovely fossils waiting to be worked on. Okay. Driftwood Canyon is a current work of one of my master students, Maria Brown. Again, those typical floras. We've got maples, we've got alders, we've got sassafras. There's our East Asian element, tetracentron, metasequoia. But we've got things like cedars and the redwood. There's our Chinese rain tree there. We've got sumac, we've got elms. What Maria is doing is similar to what Robin did for Falkland. She was attempting to reconstruct the flora through time. Unfortunately, the fossils didn't cooperate, so she's just going to do a general overview of the flora. We also did some sampling for the pollen. The pollen gives you insight into plants that may not preserve as leaves or be unrecognizable as leaves. The two are complementary sources of evidence. What is intriguing about the pollen is that redwoods are quite rare as pollen in this sequence, but are really common as leaf fossils. So it's a bit of a puzzle for us. And this is repeated in the coal where that tapir jaw came out of. That weird little 3-letter code, TCT, just paleontologist code for pollen that we associate with particular conifer families, which include the redwoods. Scarce, but again, the macrofossils, the leaves and things are quite common. Things like hickory and other relatives of the hickory and the walnuts, elms, and various ferns and other kinds of plants. So we're getting a picture of the community. Moving forward in time a little bit, last summer I was out in Kamloops region and down around Princeton. I was fortunate enough to be awarded an expeditionary grant by the National Geographic Society, so building on prior work funded by the Canadian government through NSERC. And we took a team out there and we were working. This is the top right panel there. This is the outcrop. It's about 1.5 kilometers, about a mile of road that was bulldozed through the outcrop. Not what I'd normally recommend as a fossil collecting approach, but this site was under mineral claim for about 15 years, and the claim operators bulldozed this road to improve access, unfortunately taking out probably 2/3 of the actual deposit in the process. Here's an example, fossil leaf. What we were doing there is, again, that idea of carefully sampling between layers to reconstruct what was going on. And that's work that's ongoing and not yet completed. This is the kind of thing I'm talking about. Here we have, this is depth through the rock layers, color-coded for different kinds of rocks, so our shales and our volcanic ash beds, and we find the fossil insects and fish and plants in our shales, but we need to be careful to not lump it all together as one great big mess, because we may be dealing with that ecological timescale change. So some of the work I'm doing currently with my students is to be more careful at the Maccabee site in particular to tease apart where in that time sequence we're collecting our fossils from. The reason I mention that for the context of Maccabee is there's been a lot published on Maccabee, but I'll go back one slide. They don't really know where along that 1.5 kilometers they were collecting. They didn't really care because it was all just the Maccabee collection, and that means that they're missing information on the ecosystem, the forest that once grew there, in terms of what's common, what's rare. This is the kind of way our day goes. People hewing out rock from the outcrop, following along the bedding plains. It's always nice to have a bunch of young graduate students along. They do all the hard work. And here I have one of my undergraduate students wrapping the fossils for shipping. Here's some typical fossils. Here's a nice leaf of Katsura from Japan. And there's some flowers. There's a nice leaf. And here's our day's haul lying on the hill waiting to be wrapped for transport back to Brandon. It's the kind of things we're pulling out. This is actually from older collections, but some work that just got accepted for publication. Here's a hawthorn. Maybe you've heard of the catalpa. This is a common planted tree south of us and west of us here in Drumheller. Beautiful big sprays of flowers that look like orchids. It's essentially a tropical tree, but there it was in Maccabee back then. Maples, grapes, we've got elms in there, we've got a whole variety of things. There's our sassafras again, that tree that is in the temperate forests of eastern North America and also in East Asia. So what do we do with those leaves? Well, we reconstruct climate. This mess of dots and colors here is a multivariate plot where we're looking at, we score all the leaves for things like size, teeth present, what kind of teeth are there on the margin, what's the shape of the leaf, is it skinny, is it fat, does it have a round base, a pointed base, and all this observation of leaves allows us to reconstruct climate. And one of the questions we had was whether or not it was seasonally very dry and seasonally very wet, or whether it was ever wet. And when we look at the results for this site, it's relatively warm. It's warmer than modern day Vancouver, probably like San Francisco. Summers were warm but not particularly hot, mild winters. Growing season was pretty wet. Growing season is about 8 months long, but the dry season and the wet season are not too different. So a relatively wet climate. But I'd like to put that in some context for you. So in this table, we've got modern day Kamloops, Vancouver, Abbotsford, Seattle, and Portland. And we can see that, and here's our fossil site reconstructed. And you notice there's some error values there, and there's some different numbers because there's different versions of the methods are available, and so we apply all of them to get a bit of a consensus approach to what the climate was. Essentially, it's temperate, it's not tropical, mild winters, kind of like more like Seattle, and summers not too different to the west coast. Rainfall on an annual basis about what we see across those coastal cities, very different to modern Kamloops. And our wet season, which is probably winter, pretty wet, comparable to Abbotsford. But our summer is wet, much wetter. Now, I know we interior people think Vancouver is the wettest place on earth and that the summers are really wet, and certainly in human perception it is, but in comparison to our little site in the interior in the early Eocene, that was much, much wetter. This was a really wet place in the early Eocene. So, wet winters, wet summers, a temperate but very wet climate. And I'm getting close to the end. I'm appreciative of time. Coolshana, one of these long-known sites near Merritt in interior BC. This is my collaboration with Rolf Matthews at Simon Fraser University. And again, that same story where we have time, but in ecological time, not geological time, so thousands of years. Again, we have dating it from volcanic ashes, beautiful flowers, various kinds of conifer shoots and seeds. And there's our little fern again, the water fern, Azolla. And again, showing these East Asia, North America linkages. In this case, the conifer Keteleria, but also some other members. Okay, what did we do with this information? Well, we looked at those broadleaf trees, the dicots. We measured again the sizes, the kinds of teeth they have, the shapes of the leaves. We also looked at what kinds of plants were there and their modern day climatic limits, which is one of the areas of my interest. Now, quite simply, each of these box and whiskers in these two plots, and I just picked rainfall and annual temperature, the line from coldest to warmest or driest to wettest is the total range you'd find in the modern day of, say, a birch or an alder or a fir tree. And we can do this very precisely now. And quite simply, if all of these are present as fossils in our Coolshana site or any other site, where they all overlap, that's the climate that we would propose existed in the early Eocene. And as we saw with Maccabee, fairly warm, winters and overall, and fairly wet. So a consistent story emerging from these different interior floras. Rolf is a bit of an artist. There's his smiling face. He produces artwork which appears in our paper, which will be out next month, reconstructing this Coolshana. So we've got our swamp cypresses and our metasequoia and our different broadleaf trees in this temperate climate, but mild winter, high rainfall forest some 52 million years ago. So to sum it up, these floras, as I hope I've shown to you today, have enormous potential for further work. We have these interesting connections between East Asia and North America, which has been known for a long time, but is becoming more and more well understood. We've got multiple sites. They're highly diverse and more like a tropical mountain than a mid-latitude temperate forest. We've got a wide variety of different kinds of plant organs, leaves, of course, seeds, flowers. We also have the pollen. Long history of research, but changing emphasis, changing tools, changing questions. And we have evidence to show that these were these temperate islands in an otherwise warm world. And as I've hinted at with a few slides, an emerging story of the different other kinds of animals, mammals, insects very well understood, and we're able to reconstruct whole ecosystems. I'll close with this and open myself up for questions, but this is my crew from last summer. There's my grad student, Christopher West, and current honour student, Marcus, who was there as a field assistant, Jalen Eberly, who'll be familiar to some of you, Bruce Archibald, Fossil Insects, my longtime collaborator. And we also had, on this particular expedition, some local lads from the Bonaparte First Nation and working with us. This is Sheldon Leahy. Sheldon's dad was working on the Maccabee site, employed by the mineral claim holders, and sadly he passed away last year, and it was a delight to have Sheldon join my team for a week working there, and delightful young man. Thank you. Oh, and I should say, thanks to Jim, thanks to Pat, and the Tyrrell Cooperating Society, as I mentioned at the beginning. Thank you.